We're going to have a look at the position of equilibrium again and how it changes, this time with respect to Kp. So with pressure, let's take an example here. A changing into B plus C, okay, hypothetical gases. We have an equilibrium expression for that, which we use Kp for, and we say the partial pressure of B multiplied by the partial pressure of C over partial pressure of A equals Kp. And again, this is absolutely true at equilibrium. And obviously, if we increase the pressure of one or the other of these gases at a time, it will have an effect on the value that we get out of this fraction. And again, the point is that equilibrium is reached when the value of this ratio equals Kp. So let's take an example. I've just set the partial pressure of each of these at one arbitrary unit of pressure. So we end up with 1 times 1 over 1 to give us a Kp of 1. It's unitless because I've just used hypothetical gas pressures. So let's say I double whatever this pressure represents. We've got 2 times 2 over 2. You can see that actually the fraction isn't worth the same anymore. Because we've got more molecules of gas on the right-hand side, doubling the pressure is going to mean a shift in equilibrium. We are going to take our new value of 2 and we are going to change it back to Kp. How's that going to happen? Well, K is now bigger than Kp was, and so we're going to have to reduce the amount of B and C, and we're going to have to increase the amount of A. And this doesn't have to satisfy the numbers, by the way. This happens because the equilibrium is attempting to reduce the pressure back down. We have put a change in. We have increased the pressure. The equilibrium is trying to respond to that by decreasing the pressure back down close to what it was, if it can. All the numbers are really showing us is that the ratio of products to reactions is the same at equilibrium when you change the pressure from one pressure to another, and concentration in the case of Kc from one to another. So let's say this one. So we're going to use up, because the K is not equal to Kp, we know that a shift is going. We're going from 2, we're taking B and C away to make smaller numbers, we're making that into A, that will make a larger number. We're going to end up with Kp of 1 again, which means that we have reached equilibrium. And again, you can see we said it would shift to the left. You can see that we've gone from a larger number to a smaller number. So if you remember from the number line, the further we are going to the left on the number line, aren't we, from 2 to 1? Okay, so we are shifting it to the left as we would expect. This is another example. This one, you might be looking at this and you might say, well, A plus D goes to B plus C. There's no difference in number of moles on each side of this equation, so surely pressure shouldn't affect it. And you're absolutely right. If we take Kp as that, we can demonstrate that I've taken the pressure of B and C to be 2 here. I've taken the pressure of A and D to be 1, but it works whatever numbers you put in. You can find that we could demonstrate that Kp equals 4 here. Arbitrary numbers, arbitrary equation, I haven't bothered to put any units in. So let's say we double the pressure. You can see that because we have the same number of gas particles on the top of the fraction as we do on the bottom of the fraction, they're not raised to any powers in this case, but even if they were, as long as the same number of moles is present, of gaseous moles is present on the top as the bottom, you will end up with the same value of Kp. So the equilibrium does not change. Final example, let's take this one. 2A goes to B plus 2C. We've got this is the Kp expression, and I've put in some arbitrary values again. 1 multiplied by 1 squared over 2 squared gives us a Kp of 0.25. This time that's half the pressure, and you can see that again I've changed K to less than Kp, so we're going to need to raise that. And so what are we going to do? we're going to need to cause the equilibrium to shift so that the number is larger, and therefore we're going to need to have more B and more C and less A. And again, the driving force behind this is pressure. We have half the pressure. The equilibrium will respond by trying to raise the pressure, and so we end up K is not equal to Kp here. We are not in equilibrium. We will shift from 0.125 to 0.25, and therefore we're going to shift this equilibrium to the right, which is what you would expect if you look at the equation, because we have more gaseous molecules on the right. So A is converted into B and C, and you can see I've raised the pressure B and C, and the pressure of A, partial pressure of A, has gone down to give us Kp again.